Now, with that in mind, how do you do this? This can be done in a group in terms of random elements. So here's the idea. Suppose you have a group property, and G is a finitely generated group. We want to measure we want to determine the measure of the set of elements which satisfy P. So we want to look, let's say, in a free group. What's the probability that if I randomly pick an element in a free group, it's primitive, part of a basis? Well, it might make some sense to say, well, primitive elements are rare, so it should be 0. Okay? But there are things that might not be 0. So what we do is, for each positive integer n, we let Bn be what's called the n-ball. And the n-ball in a free group is all the elements, in terms of a generating system, that have length n or less. It's called the n-ball. Now that's a finite set. So we can actually measure the real probability that an element within the n-ball satisfies property P. Okay? So then what we do is, let's call that S intersect Bn. We find the size of that. These are finite numbers. Bn, this is a finite probability. We take the limit as n goes to infinity. Now that might not exist. There's no guarantee that that limit exists. But if that limit exists, we say that that number is the asymptotic density of that property. Now, if the asymptotic density, I'm trying to get away from that.
You look great, Dan. What are you complaining?
If the asymptotic density is 1, then we say the property is generic. So a generic property is a property whose asymptotic
But isn't
density.
there's an example of a measure that you can put on a group
Oh,
where the generic group is finite.
Oh yeah, there's a.
I mean,
there's
so
a
it doesn't
different
just depend on
what's his name? Olshansky put measures on. The famous thing is what's his name? Who did? I'm getting sick. Gromov. Gromov has one measure for every group. The probability that a group is hyperbolic is 1.
Yeah.
Right.
But then he has another measure where the probability that any group is hyperbolic is 0.
Exactly.
So it's tough. This is all relative to whatever measure you choose on the
Yeah,
group.
but that creates a serious problem, I must say.
Recently, Ventura and Pascal proved that generically groups are trivial.
Yes.
Yeah.
Exactly.
Well, in a certain sense, the following would make some sense. Generically, every group should be a free group, rather than trivial. You see, trivial would imply that the relations kill off everything. But in most groups, the relations aren't going to do anything.
Wait. Generically, every group should be free. There are
Exactly.
uncountably many
Yeah.
groups.
Yeah.
There are.
Yeah, but generically it should be free. But there are many measures. Way, who you mentioned, Pascal Way, they proved, for example, that, I forgot what it was, there was an element that we could prove was the opposite of what they did. It was 1 for their measure. And what happened is the evidence seemed to prefer my way. But my evidence preferred my way or whatever. But the fact is that it does a question there. But here's the point about this. We say that a group has the generic free group property if finally generated subgroup is generically a free group. Now there's a result of Epstein which says that in the group GLN-R, and that's R is the real numbers, the probability, not generic density, the actual probability using measure that a group that a finitely generated subgroup of matrices generates a free group is 1. I'll give you a proof of that. It's very, I don't know if he did it that way, but I put this in a paper, and it's.
This is famous. This is famous. This is a rather famous.
It's a famous result,
I mean,
but I'm not certain how they know the paper.
The group theorists, they've been aware of this.
They use it all the time. It was 1980.
Yeah, I mean.
But essentially, we say that a group satisfies the strong generic if the random elements you pick don't only generate a free group, they actually are a free basis for the free group. Now, yeah, that, I think Alexei in his papers calls that the dominant Nielsen property. I called it strong generic property. But here's the result we need for the password security. Jitsukawa, who was a student here, right? Did he finish with you guys?
Probably before.
Well, he was a student of Alexei, so it has to be before Alexei. But Jitsukawa proved that free groups themselves have the strong generic free group property. Now, you might say, that has to be true because of Nielsen-Schreier. But not so. You see, Nielsen-Schreier says what? Nielsen-Schreier says any subgroup of a free group must be a free group. So if you take n elements, they have to generate a free group.
Right.
But it doesn't say anything that those are a free basis if you randomly pick it. And Jitsukawa proved that if you randomly pick n elements in a free group, they are a free basis. But that's exactly what we needed for the random security of the password system, because if we pick challenge words, they randomly check, do a free group. When we pick out new random words, those together with these generate a free group. So you're getting no homomorphic information by collecting things like that. Let me finish, but I was just going to finish. Yeah, because it's too long. I'll give you, I was going to say what we needed to actually implement this system. But rather than that, because it's really nice, I'll give you a proof of Epstein's theorem. It takes like 30 seconds. So, whoops, no, this way. So this guy Epstein, who was also South Africa, I found out that he and Gilbert were on the same plane from South Africa to graduate school.
And didn't know.
No, they knew each other. They
Oh,
hated
I
each
see.
other or something.
Yeah.
Yeah, but that's what he told me. But how does Epstein prove this? And this requires a little thinking. This is actually probability. So consider the set of all n by n matrices over the reals. Okay? Now what do they look like? They look like n squared tuples. Right? It's n by n, it's n squared tuples. So the set of n by n matrices over the reals looks like n squared dimensional real space. Well, you can put a measure on that, just like you do in measure theory or whatever. So there's a measure on that. Now, what things are in GLNR? Well, they're in GLNR if they're invertible.
Correct.
Which means that the determinant is non-zero. That means they're not in that if the determinant is zero. But the determinant is a continuous function. And zero is a single number. So the measure of the elements that have determinant zero is zero.
Equal to zero, yes.
Okay? So that says the measure of GLNR is exactly the same thing as the measure of the whole space. Okay, so far so good? Now, pick out n elements, any n matrices. Okay? And let's assume that those n matrices satisfy a non-trivial relation. So the group isn't free. Okay, can you figure that?
Then that forces it under dimension-wise.
Exactly.
I mean, I'm thinking algebraic,
That's
geometric
exactly the
about
proof.
it.
Yeah.
You take those n matrices and they satify a relation.
Then that is.
But what does a relation do? It forces a algebraic relation on the variables.
Codimension, it becomes a codimension one subvariety,
Yeah,
perhaps.
well,
yes.
no, code dimension more than one, because you may have several relations.
Yeah, yeah. Oh, I'm sorry, yes.
But what
yes.
it does is, it forces those matrices to live in a lower dimensional space.
I was thinking in terms of the trace. If you take
Yeah.
the trace of that of that
Oh, you can
equation,
do that also, yeah, but
then
just
you,
think
then
it's-
you are a
that's-
hypersurface
yes, exactly.
in a n-dimensional variety.
Yeah, well,
you know,
that's
so-
it.
and
No,
then-
the point is that if you took these matrices, the elements have to live in a lower dimensional space.
Yes.
But whatever matrix, whatever measure you put on Rn squared, a lower dimensional space has to have probability 0, or measure 0. That does it.
Beautiful.
It's a beautiful idea, really. Here's another amazing, of the same proof. Now, I don't know, I'll give you the last thing. I don't know how many of you teach linear algebra.
Unfortunately,
Yeah,
I have
did you
taught
teach
linear
linear
algebra many
algebra? No.
times. My
Okay.
students hate it.
Are you teaching linear algebra?
Yeah.
Okay, so now you're in linear algebra, and maybe you have a lunatic professor who never shuts up or whatever, but in linear algebra, let's say you want to show the technique that, to test independence of three vectors, say, in R3. Well, what do? You take three, and one of the things is, if you teach it, you go, well, I'm going to randomly choose these three vectors. Almost always, you come up with their independent. You know, you say, okay, I'm going to give me one three vector, give me two. You do, they're independent. That's the same proof. Because they're living in 9-dimensional space. They're living in 9-dimensional space. If they were dependent, there's a relation on them, and they live in lower space, which has probability 0. So some people don't understand it. They go, how come every time I do that, I get them to be independent? Why can't I randomly fix it? And it doesn't work because of the probability there. Okay, I guess that's it. So, sorry to go over.
Any question? Do you
Nobody
have
wants
any
to
question
ask
for us? Ben?
Let the- yeah.
I guess, Ben, with respect to utilizing this, I guess keeping it at home will be very safe because someone can just hack into your computer and get the group. So.
Well,
Military usage or something.
well, that's the same thing. You should have really a handheld device. But to get it, you might need a password to get into your device, a different one. So, I mean, it's not 100% safe. None of these is 100% safe. But right now, if you're doing banking by home, all you need is a password. So if they hack into your computer now, it's even easier.
Mm-hmm. Absolutely.
Do you follow what I mean?
Yeah.
We solve problems only to create new ones.
Yeah, well, look, if, what I told you earlier, if they build a quantum computer, then we're really in trouble, and we're going to have to use Angel Gold stuff.
Any other
So-
question? Do you have any open question for us?
In this,
Yeah?
what's the best parameters to do this? You see, we have a whole bunch of questions on this. These are things to perhaps to think about, you see. Here's the actual implementation. What's the rank of the free group? How many variables you can have in there? If you have too many, the program gets too big. If you have too few, it's too easy to solve. Is there not? What's an enhancement program? How do we make the words? And we wrote a simple program using Nielsen transformation, but there's another way to generate your groups so that there's tremendous amounts of cancellation in the words. Choice of parameter size for the length of the randomly chosen words. Okay, because you want to make certain that your words aren't, this is the challenge words. The challenge words aren't too small, aren't too long, and so on. So, anything else? Yeah. This is the permutation system where you change the coding. How do you do that? And that's it. Oh no, automatic reset. That I don't think we can do, but I think you have to, for the reset, you have to have a face-to-face.
Thank you very much. Let's thank Ben for his lively talk.
Thank you for inviting me. And the Beamer worked out all right. This is my first foray with Beamer.
Great.
Worked out all right.
Well, they're going to be in YouTube all over the world, and you'll But you look like a giant, Ben, because of the fact that I was photographing from under, so I hope you don't mind that, okay?
Did you see the picture that they wanted to put, this volume that's dedicated to me?
Uh-huh.
Yes.
So Vladimir picked out a picture of me.
Oh,
My face was about this. Do you remember that? I said, Vladimir, please don't put that picture in. I mean, I look like...
The star, remember?
No, the star. I needed one in a hurry.